Continuing our rectilinear motion lesson, we've got our first free response question, and it is in fact calculator active. So the setup goes, a particle moves along a horizontal line for 0, which is less than or equal to t, which is less than or equal to a. The velocity of the particle is given by this v of t function. You can see it's kind of complicated. Good thing it's calculator active. And the position function is given by s of t. Well, we know it's s of t, it's not actually given to you. Anyway, it is known that s of 0 is equal to -3. There's our initial, like our starting position, 3 spaces to the left of some sort of origin point. So let's look at the different parts that we're going to have to tackle. Part A, find all values of t in the interval from 4 to 7, for which the speed of the particle is 5. Part B, write an expression involving an integral that gives position s of t. Use this expression to find the position of the particle at t equals 3. Common question types for sure. Okay, part C, find all times t in the interval between 0 and 8 at which the particle changes directions. That's going to be easy. Justify your answer. And part D, is the speed of the particle increasing or decreasing at t equals 7, and give a reason for your answer. That's exactly what we talked about with those right here, this gas pedal and brake questions. Okay, all right, so let's pull up a sheet of paper where I have this all kind of mapped out for us, and then we also want to pull up a calculator because we want to type in these equations. So before we even get started on the problem, let's say I have this calculator app. If you don't, pull out your calculator, whatever. We want to actually open up a calculator. You know, I just discovered something about this, so I'm going to do a little widget here. I'm going to do a sideways, side by side. Over here on this side, I'll do the graph screen. So I'll add a graph. Over here on this side, I will add a calculator. So now I have them kind of side by side here. All right, over here on this left side, I am going to hit the plus sign, and we're going to add in our function, which I need to pull up so I can see it. All right, we've got t minus, and of course we're going to replace all those t's with x's, x minus 3 natural log, there it is, of t plus 2, x plus 2. Okay, get out of the parentheses, and then plus 2x. Go ahead and hit your times symbol so it doesn't get confused before you hit the sign of, and then we have a fraction in here, and it is x squared over 12. Yeah, over 12. Doop, doop. Enter, bam, there it is, and there's even a graph. And then nice thing about this now is I should be able to just go over here to the right hand side and do some math on it without having to flip back and forth. Very handy. Okay, back here. Find all values of t in the interval between 4 and 7 for which the speed of the particle is 5. So I'm going to write something down before I go back to the calculator here. So we want the speed. Speed is given by the absolute value of t. What did I just say? Is the absolute value of the velocity function, and we want this to be equal to 5. Well, we're going to have to solve this on the calculator, and I think the easiest way to solve this on the calculator is to take that 5 and subtract it. So the absolute value of velocity minus 5 is equal to 0. So if we plot this as another function, so in our calculator it's going to be f2 sub of x, and then we just see where it touches the x-axis. That's what we're looking for. So come back over here. I'm going to hit the plus sign, and then I'm going to take the absolute value of the previous function. I call that up with the little vars button, and I can put a little x on the inside of it and hit enter. Now I've got, you can see that's kind of cool. It just took all the stuff that's down there on the bottom and it flipped it up above the x-axis, which is what absolute value, of course, does. I'm going to go back to this list so that I can turn off f of 1. Okay, turn off f of 1. Ooh, There we go. And the other thing that I think that I forgot to do is actually subtract 5 from this. All right, so minus my 5 and hit enter. There we go. So just moved it down. So we want all the places where the absolute value is equal to 5, and that is going to be everywhere where this touches the x-axis. And there's quite a few places, but we only want it between, I think it said 4 and 7. So yes, in between 4 and 7. So I'm just going to use the little 0 function on here. So I hit the little the toolbar, I mean the the wrench. Yeah, there we go. We're going to analyze the graph. We want to find a 0. And then I'm just going to drag this over. Let's see, that's a 1, a 2, a 3. So this first one is in between 3 and 4, so we don't want it. We're going to want the first one here, and then drag the right-hand side over here. And then here's our first value at 5.621. Write it down. So, whoops. T is equal to 5.621. I think that there was another value probably, so let's find another one. And this is going to crowd things around here, so I'm just going to move its label around. Okay, so let's find another one with a little wrench. 0. There we go. And then move the lower bound. So that one was 5, 6. So here it looks like we have another one somewhere around 6 or 7. Yeah. Okay. So the other one is at 6.520. And then let's just double check to make sure that we do not have another one. So it looks like the next one actually hits to the right of 9. So that's it. We're finished with that part of the problem. And then just officially box that answer. Okay, let's look at the next part. Write an expression involving an integral that gives the position s of t. Use this expression to find the position of the particle at t equals 3. Okay, well, we've done this a number of times, at least for, I have a rate equation. I need to work backwards from that rate equation to get the original quantity. And in order to do that, of course, I'm going to take the antiderivative of the velocity. It's going to give me the position. But I just need to put on here some limits of integration so I can actually turn this into an equation here. So at time equals 3, I'm not going to worry about that yet. I need to come back up here and actually use the initial condition which they gave me, which is this s of 0 is equal to -3. So that position is going to be our starting place at 0, and we're going to go up to, we're supposed to go up to t because we want s of t. And there's a conflict between the t that's on the top there and the t that's inside the integral, so I'm going to have to change some of these variables. I'll just change them to an x. And then we'll evaluate that from 0 to t. Using fundamental theorem of calculus, we would get s of t minus s of 0. And that s of 0 is, back up here, it's a -3, minus a -3. And then we're going to just solve this equation for s of t, piece of cake. I just subtract over the 3 because those negatives, of course, will cancel out. Yep. And then we have our function s of t is equal to -3 plus the definite integral from 0 to t of v of x dx. Okay, like I said, we've seen this kind of thing play out quite a bit, where the -3 in this case is our initial position. Right, and then the other part of this, the integral part of it, all of that is our change in position. In order to get our new position at s of t. So the question now is asking us to use that in order to find s of 3. So I'll start with a -3. Definite integral, I'm going to put a 3 in for my t, so from 0 to 3. v of x dx. Now it's calculator. So come back over here to the calculator. I can come over here to the right-hand side and just type in what we had. So 3 plus our definite integral from 0 to 3. Inside there, we want the original f1 of x, and then with respect to x. And hit enter. Oh, look at that. That's very lovely. It gives me the exact answer. Okay, so I'm going to hold it in and then get the approximate answer of negative 6.263 or even 262. Either one of those would be acceptable, which is equal to negative 6.263. So this means that it is to the left of the origin, negative position. Ooh. All right, we used our calculator on that part. Okay, moving on to part B. Find all the times in the interval from 0 to 8, at which the particle changes directions. So the particle is going to change directions when v of t changes signs. That's what we want to see. So let's go back to our calculator. And then I'm going to have to change up my graph here a little bit. I need to go back to the original graphs. So I'm going to hit the hamburger button, and I actually want to go up here and get my old one back. And so I've discovered how to do that. If I click here, I can go to the up arrow and I can turn it back on. Okay, and then I'm going to go down to the second one and turn it off because I don't need that one messing everything up. Okay, so now it's basically an application of finding the zeros of this function, because I'm going to change from positive, negative to positive. I can also see that these things are messing stuff up as well, so maybe I can get them to disappear. I don't know. Maybe not. Okay, it doesn't want to. Here, okay, maybe now I can do that. Can I? Delete. Delete, yes. So this is cleaning it up a little bit. All right, and we just want some zeros here. We do the same thing that we did before for the zeros. We're going to go to the little tool, little wrench, and why did I choose table? I want to analyze the graph. I want zeros. I move this to the left of the first one on the right, and then we can see that the first place that this thing happens is 2.340. Okay. The particle changes direction at t equals 2 point blah 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 2.341, and then probably someplace else too. I didn't even click on that one. Okay, and then there's another one over here. It's actually a third one past 9. I don't care about that one. So another 0. Oh, yeah. And then over here. And then, of course, it would overlap it, so I can't see anything. All right, 6.127. And t equals 6.127. And then I need to justify it. I need to put a reason. And the reason why is because our velocity function changes signs. Just what I wrote right up there, but I'm going to put it in my sentence. Since v of t changes signs at these times. Okay. There's my answer, and my justification. Golden. All right, we got one part left. Is the speed of the particle increasing or decreasing at time t equals 7? Give a reason for your answer. So we're just going to look at the signs. We're going to find the velocity at 7, and then we're going to find the acceleration at 7. Oh, I think there was supposed to be a 7 in there someplace. And then just check to see what their signs are. So, of course, to find the velocity function, we're just going to take the derivative of velocity. To get the acceleration at 7, we're going to take the derivative of velocity and plug 7 in. Probably said that wrong. Anyway, so coming back over here to the calculator part, the first part for the velocity, I'm given the velocity function, so I just plug in my number. So that was the first function, that was the f1 function, and I plug in, was it 7? I think it was 7, yeah. Approximate this one, and I get a negative 911, or negative 10.9112. Negative 10.912. Yeah, something like that. And the acceleration, to get that, we'll have to take a derivative. Should be easy on here. But I guess the formatting of it is a little strange. It's not straightforward if you're using this little app. I'm going to use my derivative button here. X down in the bottom. Inside here, we want our f1 of x, so choose that. Okay, but if I just do here and I stop here and hit enter, it's going to give me the actual, bam, you can see it's the actual derivative, which is not what I want. I want the derivative evaluated at 7. So the way that I do that is with a little such that. The such that is over here in the same key as the comma. So you hold it in, you can see the vertical line such that right there. And then we tell it what x value we want to evaluate it at, which is x equals 7, and now I'm going to hit approximately equal to. The little warning sign here is just saying domain of the result might be larger than the domain of the input. Not to worry, we got our value. We've got negative 10.561. Right there. Negative 10.561, I think it was. All right, so notice that they both have the same signs. Since they both have the same signs, right up here, we're hitting the gas pedal, right? They're both negative, so it's speeding up. I'm going to write the speed of the particle is increasing at t equals 7 because v of 7 and a of 7 have the same sign. That's all you have to write. Now you could say that v of 7 is negative and a of 7 is negative. That would also be an adequate explanation here. So we're saying that it's increasing with a reason that they have the same sign. Okay. All right, so that concludes your first free response question involving both the derivatives, antiderivatives of velocity, position, stuff like that. Rectilinear motion. All right, so we're going to go back to the slideshow briefly, and what I'd like for you to do on your own is the second example. It's also on your little lesson handout if you had printed it out. So take a look at this one. This one, instead of having an equation, it has a graph, as you can see. You can see that you have a graph of the velocity function, and it is calculator inactive, no calculator this time. So take about 15 minutes to work through that problem on your own. You can check your work by looking at the answer key to the lesson handout, or you can come back to the next video and I'll take you through it step by step.